It's been more than a century since the foundation collapse of the Transcona grain elevator, a legendary case in geotechnical engineering history. It's a fascinating case, and rightfully so, because of how it contributed to our approach in understanding and applying previously developed soil mechanics theory into the way we design foundations, or at least what we design for. It's a well documented collapse that you can find in soil mechanics textbooks and scientific publications. So, what happened and what did we learn from the collapse of the Transcona grain elevator? This is Geotex with Clemens. At the turn of the 20th century, Canada saw a huge uptake in wheat production, which resulted in serious congestion in the Winnipeg railroad yards during peak periods of grain movement. Construction therefore started in 1911 on the Transcona elevator in conjunction with one of the world's largest railroad yards at the time to facilitate the rapid grain movement. The entire structure consisted of a reinforced concrete dryer house, a 16-story workhouse, and a 10-story bean house. The 64 silos of the bean house were founded by a reinforced concrete raft foundation founded on cohesive clay soil. The bean house had a total volume capacity of 35,000 cubic meters. On October 18, 1913, during the transfer of grain into the newly constructed 35 million liter elevator, the bean house began to settle and tilt to the west. Within 24 hours, the structure had tilted 27 degrees from vertical, and the western edge of the foundation had sunk 7.3 meters below its original elevation, with the eastern edge rising about 1.5 meters above the ground. Earth mounds as high as 4.6 meters surrounded the structure, having been thrust up as the failure occurred. The interesting part about this failure is that the structure was entirely intact, which meant it was purely a geotechnical failure. You see, soil bearing capacity theory is relatively well understood by today's geotechnical engineers, and we have more sophisticated foundation analysis tools at our disposal, allowing us to carry out advanced analysis. This was not the case during the early 1900s when the Transcona elevator was designed and built. At the time, local experience was relied upon to design foundations. The first comprehensive total stress bearing capacity theory would be proposed around the mid century by Kautasagi. So, to really understand what caused the failure, let us take a step back and take a closer look at the soil material that the structure was founded on. You see, the significance of the failure did not escape early foundation engineers who recognized this unique opportunity to compare the loading at failure with that predicted by classical bearing capacity formulas. With that, detailed test boreholes and laboratory testing were carried out between 1951 and 1952. Based on the borehole data and lab results, the subsurface profile at the Transcona grain elevator site consisted of clay fill, followed by a layer of stiff brown clay, a highly plastic gray clay layer, a glacial silt layer, and finally, a highly fractured and water bearing limestone bedrock. These deposits were formed in the post glacial Lake Agassiz era as the glacial ice retreated up north. The compression index of the layers ranged between 0.4 and 0.75, suggesting moderate to highly compressible. Compression index is a fundamental parameter in soil mechanics that quantifies how a soil compresses under increased effective stress during primary consolidation, or the rate at which the voids in the soil sample decreases with an increase in pressure. The overconsolidation ratio ranged between 1 and 8. In soil mechanics, overconsolidation ratio is a key parameter that describes the stress history of a soil. Soils are subjected to various load and unloading conditions over time, which affects their mechanical behavior. The overconsolidation ratio is derived from dividing the maximum past effective vertical stress by the current effective vertical stress at a point. To achieve this, an oedometer test is conducted on an undisturbed soil sample. The oedometer test, or one-dimensional consolidation test, is a procedural test in which the sample is subjected to an increasing load and a displacement load curve is plotted. The curve consists of a flatter portion, an inflection point, and a steeper straight line. The flat part, or the recompression line, represents the pressure that the soil has experienced in the past. In the early 1930s, Arthur Casagrande developed a visual technique to establish the maximum pressure that the soil has been subjected to in the past. To get this, first we determine the highest point of the curvature on our inflection zone. Then we draw a straight line. We then draw a horizontal line from that same point. Secondly, we bisect the angle created by these two lines. And finally, we draw a straight line along the straight portion of our curve. The estimated pre-consolidation pressure is at the intersection of these two lines. On the other hand, the current effective stress is determined by multiplying the unit weight of the soil and the depth to which the sample was collected. With the pre-consolidation pressure and the current effective pressure at the transcorner site determined, the upper brown clay had an overconsolidation as high as 8, and it reduced to 1.5 in the lower gray clay. So here's a widely accepted theory on exactly what happened. The Met Foundation had been adequately designed to tolerate large settlements. You see, during construction, the engineers had determined that the founding materials were uniform and sufficient to support a fully loaded bin house using plate load tests, a method which was widely used during that time before the current in situ test methods were introduced, which are capable of evaluating soil strength in deeper strata. The method is very useful to determine the ultimate carrying capacity of the soil. However, it has a critical shortfall, which proved disastrous in the case of the transcorner grain elevator collapse. To visualize how stress is distributed under the foundation, in 1885, Joseph Valentin Bozennesc developed the concept of stress influence bulb. The analytical solution shows zones of equal stress beneath the foundation. The zones of influence are proportional to the load and the size of the foundation. So, when the engineers used the plate load test, all the stress was distributed in the upper stiff brown clay, and they determined that it was capable of supporting 1.3 times the expected fully loaded bin house. But the stress bulb of the actual bin house extended deeper into the lower gray clay, where the foundation load exceeded the pre-consolidation pressure, triggering the failure. In addition, although it was reported that the bins were uniformly filled, the possibility of eccentric loading cannot be overlooked. Even a small shift in the center of mass could have introduced a moment force and caused an uneven load distribution under the Met Foundation, initiating the failure on the western side of the bin house. The failure followed the classical Terzaghi failure plane as evidenced by the soil mounds thrust up around the collapsed structure. Due to fears that the foundation of the workhouse might also collapse, in December 1913, the Foundation Company of Montreal and Vancouver submitted a plan to underpin the workhouse. They sunk piers into bedrock under each building column. Since the bin house structure was intact, the foundation company convinced CP Rail that it was possible to salvage the bin house by righting it and underpinning the structure once the vertical position had been reached. This was a daring proposition for its time, considering how heavy the bin house was. Initially, a trench was excavated along the entire east side of the bin house to the underside of the Met Foundation. Drifts were excavated beneath the Met foundation, and a row of 14 piers was sunk to bedrock along the west edge of the Met foundation. Wooden rockers were then attached to the top of the piers. The intent was to support the structure, with these piers acting as a fulcrum about which the structure would be rotated. Shoring timber screws were installed on the western side of the structure. These were used to support and push the beam house to the west as the soil under the beam house was being removed. More piers were sunk to bedrock along the drifts, which would support the building once it was in its right position. On October 17, 1914, the beam house was back in its vertical position, having been raised about 3.7 meters in the process. Though the beam house could not be retained to its original founding depth, this was a highly successful operation that will remain written in the history books. While today's standard of practice would have easily predicted the outcome, such was not the case in the early 1900s, when an observational approach was often relied upon. It was a time when lack of understanding of soil behavior could be offset by reacting to the problems with ingenuity and determination. A study published in 2019 to replicate the failure using a coupled analysis concluded that the failure could have been avoided if the bins had been filled in stages, allowing the poor water pressure in the saturated grey clay to dissipate and consolidate the soil. But hindsight is 2020. The concepts of staged loading and stress parts would not be recognized until decades later. You've been watching Geotechs with Clemens. If you found this video interesting and entertaining, please leave a comment in the section down below. Thank you. Until the next one.